Hello everyone, in this section we're going to talk about divisibility. So by definition, if you have two integers and you say that d divide n's, then what you have is that n is going to be equals d sometime some other integer. Notation wise, this is read like d bar n, and it's read d divides n. You gotta be careful with not confuse it with is divided by. And here, this is another really way of saying if d divided n is because n is a multiple of d. That's what you're really trying to say. So d divided n mean n is a multiple of d, and hence is going to exist a k that belongs to the integers, so that n is d times k. Now, an alternative phrasing of that will be n is divisible by d, or d is a factor of n, or d is a divisor of n, or n is a multiple of d. This is all the ways that you can represent or say this. Now, let's give some examples. So, 4 divisible by a means that 4 divided a, and this is true because we can represent a as 4 times 2. So you can see 4 divided 8 because there's a multiple between 4 and 8. Now, this other symbol with the slash, this is 4/8, which is 1/2, is 0.5. This is actually a number. This is a fraction, a quotient. This is completely different, okay? So every time that we have this bar, we're talking about this relationship with the multiple. Now, the correct usage here will be something like this. So, for example, we can say 5 divided 15, and this is true since 15 can be seen as 5 times 3. There's going to exist 3, so that 5 by 3 is 15. So, because of that, we have that 5 that 5 divided 15. Now, 4 doesn't divide 6. So the 4 divided 6 is a false statement because there is no integer, so that 6 is equals 4 times k. So in this case, we don't have divisibility between 4 and 6. So 4 does not divide 6. Okay, it gotta be an integer. Now, one question here, does 3 divide 39? The answer, well, we will need integer so that 39 can be represented as 3 times k. Can we solve for that? Yes. Actually, the integer 13 is going to work out, and then we have that 39 can be represented as 3 times 13, and we confirm the divisibility of 39 by 3. Now, does 4 divide 6? Once again, we will need that integer so that 6 can be 4 times k, but that's not going to happen. If we solve this equation, we get k is equals 6 over 4, which is 3/2, but this is not an integer, so it's not going to work out, okay? So hopefully that clarifies better when the divisibility doesn't happen. Now, is 0 divisible by 2? Well, the answer is yes, because we can represent 0 as 2k, with k in particular being 0. So yeah, 0 is divisible by 2. In general, for all non-zero integers, we have that any integers are going to work out. So 0 is going to be divisible by any integer. Negative divisors are going to work too. So for example, is 7 a factor of minus 21? And yes, because you can represent minus 21 as 7 times minus 3. So when you were looking for that special k that makes it so minus 21 is 7k, you can count with minus 3. So we can have negative divisor, negative integers, and they're working on our favor. Now let's see some theorems about divisibility. So first theorem, for all integers a and b, if a and b are positive and a divides b, then we have that a is less than b. Well, this is going to be a consequence, like let's say if a and b are positive integers so that a divides b, then you have that b can be represented as a times certain k, with k being integer. So that means that you need to multiply a by k to reach b. So that makes sense that a is a much smaller number than b. In particular, since a and b are both positive, notice that k is going to be bigger than 1. Because you might be thinking, well, what about negative numbers? But the thing is, like, they're both positive, so there's no way that k is not positive. K needs to be a number positive, actually bigger than 1. If k is a negative number, then we're going to get that a times k will be negative, and so that will be a contradiction with the fact that b is positive. Okay, so that's why we don't have that k can be negative. Now, since k is bigger than 1 and a is bigger than 0, then in general we can just say, well, b is equals a times k, and that's going to be bigger than a times 1, since k is bigger than 1, and so b is going to end up being bigger than 1. Notice that we're still following the 5-step structure. It's just that we're not necessarily telling you, hey, here I'm using the assumption, here I'm using the definition of the assumption, here I'm making the manipulation, here I'm stating the definition of the conclusion, and here I'm stating the conclusion. But all your steps are in there. We're always using that structure. Okay? Now, another theorem. For all integers a, b, and c, if a divides b and b divides c, then a is going to divide c. So this is a transitivity relationship. So first, let's go with the definition of the hypothesis or the assumption. A divides b and b divides c. So that's going to mean that it says integer k1, so that b is equals a k1. Similarly, it says k2, so that c can be seen as bk2. And now, having those, then we can substitute in the first equation. We can just take c is bk2, but now we know that b is ak1, so we replace it, and now we can see c as a k1 times k2. This is going to be an integer, as multiplication of integers, and so we can see c as a k, so that's going to mean that a divides c. Okay, let's give an example of that theorem in action. So let's say if 2 divided 6 and 6 divided 18, then 2 is going to divide 18. That's pretty much the application of this. So let's verify that that's true. Well, 6 is divided by 2 because 6 can be seen as 2 times 3. 18 can be divided by 6. In particular, 18 is 6 by 3. So 6 is dividing 18. And we can also see that 18 is divisible by 2 because you can see 18 as 2 times 9. So that's going to mean, yeah, 2 divided 18. So we verify that it works. Of course, this is an example, not a proof. We do need the proof in general for different things. This is just validation with one example. Now, the general principle is that divisibility here is going to be a transitive relationship, like a change. So if a divides b and b divides c, then a is going to divide c. Now let's talk a little bit about prime numbers. So as a reason, any prime number is a number that is only divisible by itself and by 1. So now, our first theorem will be any integer n, integer in general, bigger than 1, is going to be divisible by a prime number. Okay? So this means that every integer greater than 1 is going to have at least one prime factor. This is a very important theorem. So now let me give you some examples. 12 is going to be 2 to the 2 times 3. So as you can see, this is 12 is divisible by primes 2 and 3. Here, if we take this 4 into account with times 3, then we'll be making it divisible by 3. If we take one of these 2, multiply, see it as 2 by 6, then we can say 6 as the integer that we need to get 2 divided 12. Now, 17 is a prime number, so it's only going to be divisible by itself and by 1. We can see numbers like 100 as 2 to the 2 times 5 to the 2, so 4 by 25. So it's going to be divisible by primes 2 and 5. Notice that I said 4 by 25, but I'm not interested in 4 or in 25 because they're not primes. So I'm just looking for what are the primes that are producing 4 and 25, which end up being 2 and 5. Now, this guarantees that every number can be built from primes. Now, extremely important here, given any integer bigger than 1, there's always going to be a positive integer k and distinct prime numbers p1 to pk, so that for a sequence of positive integers, I can just see that integer as a product of powers of primes. So essentially, I can do what I'm doing here, and is break down any integer in powers of primes. I have the prime number 2, prime number 5, and the power here is 2, the power here is 2. I have power prime number 2 here, prime number 3, to the power of 2 to the power of 1. So this is what we're doing here. We have distinct primes, and we have the number of powers that we're using. Okay? In simple terms here, what I'm saying is that every integer that is bigger than 1 can be written as a product of prime powers. This factorization is going to be unique, and that's very important. Up to reordering, of course, if you flip the order of 2 and 3, or 3 and 5, or so on and so forth, but the factorization is unique. Now, in the examples, once again, I can represent 12 as 2 to the 2 times 3, 100 as 2 to the 2 times 5 to the 2. At 360, I can represent as 2 to the 3 times 3 to the 2 times 5. And it cannot be factored differently. You know, you can see that at most you can permutate the primes, but that's all that you can do. Now, this theorem guarantees that primes are just going to be the building blocks of our integers, and every number has one prime factorization if you don't take into account the order. Now, one theorem that is separated from this but related will be that the only divisors of 1 are 1 and minus 1. That kind of makes sense. The idea of the proof is like if you have a number that is dividing 1, then you need an integer k so that 1 is equals to d times k. But for the product of two numbers to give me 1, there are only two options. So d times k equals 1 can only happen if d is 1 and k is 1, or if d is minus 1 and k is minus 1. So hence, the only divisors here of 1 are going to be 1 and minus 1. This is why 1 in particular is called the units, and it divides everything but has only the trivial divisor or itself. Now let's talk about some common mistakes when talking about divisibility and the misconceptions here. So you gotta be very careful not to confuse divisibility with ratios, with fractions. D divides n is a statement that can be true or false, but D divides D fraction n is just a number, it's a quotient. So you cannot ever write something like 4 divisibility a is equals 2 because you're mixing a statement with a number. This is a proposition. This is a number. Now, thinking that d divides n means that d is less than n. This is false. 6 divided 3 is false, but not because 6 is bigger than 3. It's false because there is no integer, so that 3 can be represented as 6 times k. Notice that minus 3 divided 6 is true. So if I flip it backwards, even though minus 3 is smaller than 6. Now, you can also forget that any integers divide zeros. In particular, is because you can represent 0 as any integers times 0. So this is going to give me divisibility. So be very careful not to confuse this statement with a fraction. Now, every time that we're doing proof, you got to be careful with not using the formal definition. It's like since A divides B, we can divide. No, this is not correct. Every time that you're doing divisibility, you gotta say if since A divides B, there's an integer k such that B is equals AK. You need to write the whole statement and what it means. Always use the existential definition. Now, assuming that A divides B and B divides A means that A is equals B. And this is wrong for all integers. So 3 divided minus 3 and minus 3 divided 3, but 3 is different from minus 3. So once again, this has nothing to do with the fact of being equal. There's just multiples between each other. What is the number that produces the multiplicity between them? Well, minus 1. You put a minus 1 here, is going to be enough to get you that relationship of divisibility that we have here. Now, k doesn't necessarily have to be positive. So we have this statement A divides B, and B is equals A times k for certain k that exists. There's no reason why k needs to be positive. K can be negative, 0, or positive. For example, 7 divides minus 21 because minus 21 can be seen as 7 times minus 3. So that minus 3, notice, negative number. Okay, so in summary, we introduced the definition of divisibility that we've been using tacitly along the course, and d divides n if it is an integer, so that n is equals d times k. The notation d divides n is different from the fraction d divided by n. We have the transitivity property. We have the order. If a divides b, then in general you're going to have that a is less than b. And we have the prime divisibility. Every integer is divisible by a prime. And the fundamental theorem here is going to be that every integer bigger than 1 has a unique prime factorization. So next, we're going into the division cases that we can use and the quotient remainder theorem. But let's take a look at some exercise on prime.